Hello there guys, welcome back to another video. Now this is the mock review. Make sure that we full power pen and full explanation for working out. Now the mock is only one paper, so pretty much all the content for paper 1, paper 2 are included in this one. Now you need to make sure that you know where the equation sheets are going to be. Now equation sheets are given at the back, so make sure that that's the first thing to check. So all the equations were given to you, so you need to know which equation to pick and how to use them pretty much, yeah, because all calculation questions will be about 3 marks. So if you pick the right equation, if you put the numbers in the right place, then that should be free, easy mark for yourself, yeah. And three marks is good in the long run. Now, the first one is the multiple choice questions, nuclear fusion. So this is fusion, yeah. It's a process that releases energy. Now, which of these statements applies to nuclear fusion? Now, let's go for the first one. Now, it emits nuclear daughter nuclear. Now, this one here is for fission. Okay, so this is when large nucleus is split into two smaller ones, releasing energy. Now it is a controlled change reaction. Now change reaction. This is for fission as well. Now it produces radioactive waste. Okay, it produces radioactive waste. So this will be also nuclear fission. Now it requires high temperature and pressure. So this is the answer. So this is the answer because to fuse things together, especially if you have hydrogen and hydrogen. Now hydrogens, they are pretty much proton, yeah, proton. So protons are positive. So to fuse these together, you need high temperature and high pressure because you want to overcome the repulsion force between them. Because these two guys, when they get close together, they want to repel each other because they're both of the same charge. So therefore, you want high temperature. So therefore, they go very fast and high pressure. Therefore, there's much greater force there. Okay, so the answer is D. Now, in the star, in the sun, we have 4 protons. Start the 4 proton again, so 4 proton, so which is 1 hydrogen, so 4 hydrogen atoms, as 400 nuclei. Sorry, it starts the process. Okay, so we've got all these things here telling us that they produce helium nucleus. They're telling us that the mass is smaller than the 4 proton. There's a mass, so the mass deficiency is turned into energy. Now the 4 proton, and the mass nucleus. So what we have is we have 4 proton at the start. So 4 proton, so 4 proton, so 4 proton, so 4 hydrogen pretty much. And this, when they fuse together, so we've got 4 proton, 1, 2, 3, 4. So when they fuse together, we eventually get helium. Okay. Now helium, the mass of the helium, you can actually see it is less. So 6.4. This one's 6.9. So therefore, there's a missing part, and that missing part is gone into energy. Okay. Now the question is, calculate the percentage of the original mass that has been converted into energy. So therefore, what we need to do is we want to know how much of the original has turned into energy. So therefore, what we need to do is we need to work out the change. So therefore, we need to find the change in mass divided by the original mass. Now, and this is in percentage because it's written there. So therefore, we need to multiply this by 100%. Therefore, the change, how do we work out change? 6.69 times 10 to the power minus 27 bracket minus the mass of the helium atom divided by the original one. Now you notice that I'm using brackets. Why am I using brackets? It's because sometimes the calculator will messed up the bod mass. So the bod mass. Okay, if you remember, okay, you need to do like I think what was it? Yeah, you need to do multiplication first before you do addition and subtraction. So what would happen is your calculator, if you don't put the bracket in, your calculator may mess it up. Okay, now plug this in, multiply by 100%, and the answer we get will be, if I use my calculator, I'm going to get my answer to be 0.75 there, and this is the answer, 0.75. Now this is already in percentage. Why? Because I've multiplied by 100% there, and this is done. You can see 3 easy mark for calculations. Now this is just a change, so this is something that you guys done in maths already. Let's move to the next one. Now estimate the difference between line P. So we've got P here and we've got P here. Inspection from distant galaxy and the Earth. So we need to do this one and this one. So we need to work out the difference in this case. All we have to do is if you zoom in, okay. Now we know that this is 400, this is 500. So somewhere in the middle here, we're gonna have 450, isn't it? And then somewhere in the middle here, we're gonna have 550. Okay. Now you just look where it is, P. Okay. So line P, think like P. So this is line P, and this is line P. Okay. So line P is, you can see that line P is very close to 500, isn't it? So what I can do is I can say that line P is at maybe 490. So this is going to be 490 there, and this one is just on 550. So therefore, the difference would be okay. And then you just use a calculator, okay, and then this will give me 60. And this is just the answer straight away. Because why is this the answer? Because this here is already in nanometers, and this is nanometers. There you go, done. That's it. Nothing crazy, and that's one mark. Yeah. Now, this is the good thing we need to know. Scientists have discovered light from distant galaxies have spectral lines shifted to the red end, so they've been shifted to the red end. And explain how redshift in light received from galaxies at different distances tell us that the universe is expanding. Now, how does it tell us that the universe is expanding? Now, first of all, we want to know that redshift, where is it? This here, what does it tell us? So it tells us that galaxies, okay, must be moving away from the Earth slash us. Yeah, that's the first mark. Okay, because the fact that they've been redshifted tell us that they are moving away from us. Okay. Now, what else do we know? Okay. Now, further galaxy. Wait, let me just rephrase this. Okay. The further the galaxy, okay, the galaxies is equal to more redshift. Okay, so therefore, if the galaxy is further, then more redshifted. So the more would have redshifted. So therefore, this here, this black line would have shifted to more to the right. Look. Okay, so that's why distant galaxies further to the right. Okay, and this tells us, lastly, this tells us that more distant galaxies are moving at a faster pace. Okay, so this will link with this one. Yes, we know they're moving away from us, but the fact that they are more distant tell us that they are moving at a faster rate. Okay, so this is where you're going to get your 3 marks from. Now, here is a parallel circuit. Okay, now we need to remember the rules for parallel circuit. So rules, parallel circuit. So what happens to current in parallel circuit? Current splits up. So this means that this current here goes through, and some will split up down, and some will split up there. And you already know how much split up. And what happens is when they go through, at this point they get added up, and then they go back again. So therefore P is going to be 0.05 plus 0.05, and this will be what? 0.1. Okay, so you can actually see this is just easy. Let's say this, the answer is B. This is just one easy mark there. Just remember the rules, yeah, and we apply the rules with numbers and done. Okay, so this is something we did last year, year 10 again. So you need to make sure that you remember the rules. And here we go again. So we have 1 mark to draw voltmeter across the resistors. Okay. Now let's take we've got 4 identical resistors there. So for all those 4 identical. Now students want to measure the current. Measure the current from this power supply and potential difference across resistors. Now resistors is S there, so you want to know the resistors across the S. Now there are 2 ways you can do it. Now all this here will have, so these guys are in parallel now. Okay, so these guys here Okay, so I'll say resistors. Okay, they are in parallel to each other. Okay, so this means that the voltage equal to the same across each other. Now I can do it this way, so connect a voltmeter here. Again, the circle V, go back, circle there. Now I need to be careful because there's an overlap line there, so I need to get rid of that. There we go. I need to do it properly, so therefore there's not overlapping anything, so I can do it like this. So therefore the voltage here across this one will be the same here, will be the same throughout, because they are connected in parallel. Okay, that's one way to do it. And then, or since I'm just measuring the voltage there, yeah, so all of them have the same voltage. Yeah, that's fine. I can even put one here as well. Okay, put the voltage across there. Right, because the voltage across these guys will be the same. So all the way throughout these things, whatever this is, so this would be like a big component there. Okay, and I think I can even connect it all the way. So if I do something like this, so from here down here across potential difference, the voltage should still be the same in this particular case. Okay, let's zoom out. Let's keep going. Okay, the student remove one resistor, measures the current, and again, blah blah, and so on and so forth. So what's done? So start with 4 resistor, okay, and then the voltage is the same. Yeah. Now measure the third one. This is the current. Second one. So what is done? The student is removing one. Yeah, and record. Removing another one. So now we have 2 left to record. Okay, and then lastly, it left till 1 and then record, and then you can see that the current is going down. Okay, now the question is predict the current from the power supplied when there are four resistors. Okay, predict the current when there are 4 resistors. Okay, now so the current is what? You can actually see that the current is going down. So why? Because when you have these 4 resistors, yeah, the total current, the total resistance was smaller compared to this one. Now we need to work it backwards. How can we do this? Okay, now let's take what we got. Now, when we have 3 resistor, and then the resistor goes down from here to here, so the difference is 9.1. Now from here to here, the difference is 9.1. So this means that the difference from here to here will also be 9.1. So therefore, the answer is going to be 27.3 plus 9.1. This will give me 36.4. So 36.4. Okay, so this is my understanding, because from here to here the current is dropping by this much, from here to here the current is dropping by this much, so therefore the current may be dropping there. Again, just one mark. Okay, now use the data, calculate the resistance of only one resistor. Now the equation is giving you from the back, so you need to look back into your equation sheet, okay, and find out. Therefore we're going to be using V. Let's go to I. Now you're looking for the resistance, so therefore you need to rearrange this. Look, this is 3 marks, yeah, this is 3 marks. So, and the equation is given to you, so this is given to you at the back. Okay, now let me just take a moment and go at the back and help you find the equation there. Okay, alright, let's look for it together. Here we go. So this is the equation given to you there. Okay, and then we can go back. That's 3 marks, yeah, 3 marks. Okay, because this is the 3 easy mark. So we just need to rearrange. So R equals V over I. Again, now if you mess this up, then you need to ask yourself. You need to give yourself more practice, yeah, because now we're in December now, yeah. So you'll be off for 2 weeks, and then come back Yeah, a few months time you're going to be on exam leave again, so we need to make sure that we are focused. Yeah, so just repeat, 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 repeat until you get it, and then when you get it, you'll be fine. V for one resistor, we know voltage is just what, just 6. Okay, and current is 0.1. Now we need to be careful there. Yeah, so 0.1, we need to be careful because look at the unit. The unit is milliamps. Therefore, we need to turn this into amps. Therefore, I'm going to use different color pen here so you know that we are converting it into -3. And then we plug into our calculator. Okay. And I'll get 3. So this is the answer for 3 marks. Yeah, 3 marks. Nice and easy. Okay. Here we go. Move to the next one. A question: what happens to the total resistance when the number decreases? Okay, the question telling us when the number decreases, what happens to the resistance? Okay, so therefore we need to talk about that. Okay, so as the total number of resistance decreases, so we can say the total resistance increases. Okay, now how do it increases? Okay, because the current decreases. Okay, because what is, look what happened. Okay, as the number of the resistance goes down, the current is going down. This tells us that the total resistance is increasing. So resistance needs to go up. So R need to go up, and then current goes down. And the last mark we get when we say the voltage is the same. You can see, look, 3 marks, 3 bullet points. Yeah, and look at the voltage. The voltage staying the same. Okay, here we go. Right, now we have moments to this question about moments. Now, calculate the moment apply again. So this one, where is the equation? Right, we're going to take a moment. Let's go backwards to find the equation for you. Okay, I'm just going to do this a few times until we get what we need to get. Okay, moments. Okay, moments. Here we go. Moments there. Look, here's the equation. Here's the equation. It's not given to you here, but it is there. Okay, so if you're taking GCSE physics, you also need to know these extra ones. So moment is force times distance perpendicular, normal to the thing. Okay, let's go back quickly. Here we go. Let's do this. Moment is force times distance. Force 28. Distance from the wrench is 15. So this is going to be 0.5 there. So therefore, the answer is, okay, so 40.2. Unit for force is Newton, and we multiply them together, multiply by the distance, so nm. So therefore, m multiplied by m. So therefore, just nm. So the answer is just nm. So look, you're multiplying them together. Yeah, the force multiplied by the distance. So therefore, Newton meter. Now, what can we do? So the first one is, so what things have a moment? So the force is 1, and the distance from the pivot. So therefore, what we can do, we can increase. So we can say apply a larger force. Yeah. Right. Apply a larger force. Okay. We can also say, okay, apply the force further from the nut. So this is pretty much saying increasing increase the distance, okay, from the nuts. Okay, so this will increase. So therefore, this is the nut, yeah. So you want to increase the distance further from it. So therefore, maybe here, and then you apply the force. It'll be much easier. Yeah. So these are the two. 3 marks there. Okay. Now what we have a, okay, 90 degrees. Right. So 90 degrees. Okay. Anyway, the force applied for the distance is equal to a quarter of a semicircle. So a quarter of a semicircle, the radius is this much, the radius is this much, so therefore this needs to be converted into this straight away. Okay, and then calculate the distance applied. So therefore the distance is the circumference. So therefore the distance is the circumference, which is 2 pi r. Okay, so therefore we're going to do 2 pi r, 0. This is there. This will equal to, let me just use my calculator very quickly. So this would be, okay. Oh, alright, so the answer is already in meters. Okay, so the answer is already in centimeters. So therefore, okay, what I'll do, I'll just, yeah, let me just keep on going. Okay, so this is my answer there. So meters. Now it tells me it's a quarter, so therefore I will multiply this by a quarter. So this will give me 0.36 meters. We need this into centimeters, so multiply it there. So therefore this will be 23.6 there. Okay, here we go, done. Okay, calculate the work done. Now the work done again is given to you in the question. So work done is force times the distance. The force is, we know force is 28, and the distance we know is this one here. Now we need this. Now we need to convert this. Yes, therefore the one I'm going to use is going to be this one. So this is the one we need. It's going to be 0.36. Okay, so therefore this times the force, so this would be 6.6. So 6.6 over there. Okay, so 6.6. 3 marks again. 3 marks. Look, 3 marks. I'm just using the equation from there. Yeah. Now we need to convert here because the answer is in joules. So we need to convert this to correct. Now, okay, it's rubbed. So whenever it's rubbed, it is by friction. Yeah. So rubbing, friction. Yeah. Now the polythene becomes negatively charged. Okay. So which of the statement is true? Now, if we got the polythene rods here, if we got the rods, and the rod's negative, this means that we are, by rubbing it, we are giving it electrons. We're giving it electrons. So which answer is correct? Which answer is correct? The answer that's correct is going to be A, because it's gaining electrons. Now it doesn't know protons don't move. Protons don't move. Yeah. So if you look at the nucleus, you've got nucleus there, which is in the center. You got the electrons that's around it. Ask yourself, if you're rubbing the atoms, you're rubbing anything, which one is easier for them to move? It's the electrons, on the outer shells. Okay, move to the next one. Which one is the anomalous results? So polythene. To tell us it's polythene, so therefore look at polythene. Okay, we got 61, we got 80, we got 59. Now 59 is closer to 60, so therefore the answer is this one. So circle it. Okay. Now, how can the student deal with this one there? Okay, the student can ignore the result. That's one thing you can do. Okay. Alright. Right. Ignore it. The student can pretty much not include that data in the mean. Okay. Now calculate the mean. Here we go. Now look at this. This question is 2 marks. Yeah. We've already say that we are ignoring the results. Now we need to calculate the mean. So therefore we got 61. So we got minus 61 plus 51 minus 51 divided by 2, because there's only two results. Yeah, there's only two results. Okay, so 61, 51. So this will give me 60. So the answer is just 60 there. Okay, here we go. 2 marks done in the pocket. How easy is that? Now, describe how a student can use a rod to just demonstrate to use the rods to show that there are two types of electric charges. So two types of electric charges. Okay, now how can we do this? Let's think of that. Okay, now what we're going to do, we're going to do something simpler. And let's see what we do. We can do the thing with the, let's do the thing with the water, because I think that's the one we've done before, isn't it? So we have a tap of water here. Let me draw a tap. Okay, now we've got the water running. Okay, now what we do is we have the charge rod. So first of all, we need to charge the rod. Okay, so we're going to say okay, so we're going to say let's have a look. Using friction, charge the rod. Okay, so therefore the rod gains electrons, therefore it becomes negatively charged. Okay, now that's what negatively charged. And then what we're going to say is we're going to bring it close to a water stream. So here we've got the water stream. Okay. Right. How many marks is this? 3 marks. Oh, okay. We need to show that. Unfortunately, we have to show these things. Okay. So the water streams bends. The water streams, stream. There's only one stream. Stream bends as there is a force, okay, between the stream and the negatively charged rod. Okay, so there's force between them, right? And then we can go into much details, right? Now, what's going to happen into the rod? So the negatively charge will repel the negatively charged in the rod, yeah? And then, so this side will be left positive, okay? And this side will bend towards the water, okay? So therefore, what we're going to say, okay, the charge rod will affect the distribution of charges in the stream. Okay, so negative charge will repel. Okay, repel, and positively charge will be attracted to the rod due to unlike charges. Okay, So the stream bends towards the rod. Okay, so what we're doing here is so we got these 2 points. So this is where we start. We have a rod that's negative charge, we have water stream that's running, and then the second thing is we have, when we bring them together, there's a force there. Yeah, there's a force. Now we don't know what that force is. We know it bends. We don't know what that force is. That is a force. What force is it? We don't know. Okay, it's attraction force, is it repulsion force? We don't know yet. And then what happens is, and then the last point we talk about is pretty much the rod is going to affect the charge distribution. So all the negatively charged will be repelled. Okay, why will you repel? Because of light charges repel. Yeah, because the rod is negative, so it's going to repel the negative one because they are the same. And the positively charged will be repelled because unlike charges attract, so that's why it bends towards it. Now what we have Hooke's law. Now we want to obey Hooke's law. Now we're going to do is we're going to keep it simple. We're going to do extension there, we're going to do force there. Okay, now we want it to obey. So what happened is force is direct proportional to extension. So this will straight line, 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 straight line. Straight line, straight line, straight line, straight line, straight line. Yeah. Now, this graph here is a straight line graph. You go through the origin, the straight line graph. So this obeys Hooke's law. Now, you reach a point here. We call this point limit of proportionality, limit of elasticity. So after this point, what happened is it will no longer go back to its origin shape. So therefore, the graph is going to curve here. Now, what happened is this means that at this point, when we apply a small force, the device, the material extend largely. So think of a string gum, for example. String gum, yeah. Let's say you have a string gum, and then you stretch it, and it gets very, very thin. Stretch it, get very, very thin. You get to a point where a small force is enough to make it even longer. Yeah, to even get it even longer. That's what's happening here. So it will obey it as long as it's within the limit. Now, so this is the graph that we need to say. We need to label it to show where the limit is, but the question just wants us to draw a graph where it is within the limit. So therefore, this is optional. So therefore, the ideal graph would just be something like this. Here we go. So this is the ideal graph. Done. So this here obeys Hooke's law. You need to label, and so on and so forth. Now, the axis can be swapped. Yeah, but we need to be careful with the beyond. So I'll leave it there. The 3 marks. Look, labeling that straight line. Again, use a ruler. Okay, nice one. Okay, right. Now, resultant force. How do we work out resultant force? What we have is we have force. Look, we got this going up, this going down. So therefore, the resultant will be pointing upwards, isn't it? Therefore, the resultant will be pointing upwards. Now, how do we work out resultant force? So F would be 3.2, take away 2. This is 2.2, 1.2. So therefore, the object will still be going up with 1.2 newtons there. Okay. Now, work out the acceleration. Now, again, so this is at the back. This here is the back. Yeah, look at the back. Let me just go back very quickly. Okay, so if you mess this up, then you were not looking at the equation sheet. Now here we go. So this is what we need. Okay. All right, let's go back. Okay, because this is free mark, and this is just maths. Okay, just you understand what's happening. Yeah, the object is being released, it has to go up. There we go. So F equal to ma. Now we're looking for acceleration, isn't it? A. So A is force from m. Force. What force is this? Force is the resultant force. We already calculated it. It is 1 point divided by 0.2. This is 6. The answer is 6 there. Alright, now let's see what's going to happen. So we got the object being pulled down. Yeah. Okay. And then it still has the reaction force. Now, when you let go, what's going to happen is the object's going to go up with 1.2. Yeah. And then, so we got the spring there. Okay. What's going to happen is over time, so it's going to go up. and then it's gonna start stretching again, and then it's gonna start going back until it's pretty much stopped. So what happened is the extension, you can see, okay, is getting shorter. Yeah, the extension is getting shorter. So the first thing we want to know is talk about the acceleration. Okay, what's going to happen to the acceleration? Now, acceleration is going to decrease. Acceleration decreases, okay, to 0. Why does it decrease? Because you let go, you pull it back down, and you release it, so it goes up, and then it goes up at, look at the acceleration, it goes up at, we already calculated it, 6 meters per second squared. And then it goes up, and then it starts to go down, and then just gets smaller, and then pretty much the thing gets smaller, and smaller. The second one is what happened is the extension decreases, because earlier you were pulling it down, so you were holding it, and when you let go, it goes back up, and then it eventually comes back to its original shape. So therefore, its extension decreases. Okay. Now, since the extension decreases, what's going to happen is the resultant force. So this force here is 1.2. What happened to it eventually? Because you're going to stop. It decreases till it reaches 0. Why do it reach 0? Because we know that the object goes back to its initial resting place. That's what happened. Done. Now this one here, this one was a nice easy question. There's on 4 marks. Yeah, solid. The particles need to be touching each other. Okay, oops. Again, no gaps between the particles because solids, they are fixed position. Yeah. Right, let me just pause the video and come back once it's done. Alright, now the solid particles, they need to be in a fixed shape. Okay, fixed shape, fixed position. They need to be tightly packed together. Look, there's pretty much no space between them. All the particles are squeezed together. Yeah, all of them are squeezed together because that's a solid. Yeah, that's a solid. Now, liquid need to have the ability to flow over each other. They're still touching. Yeah, so they still have the molecular bonds, but they're very, very weak. So it's still there. So the way I'm going to draw it will be the following. They still need to be able to flow over each other. So we've got this there. Okay. So again, they need to be they're still touching with each other, but they need to be what? They need to be randomly arranged. Therefore, they're touching each other. So let's do it this way. Okay. 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 Here we go. Go. 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 They're still touching, but random. Right, you can see a pretty much random direction there. Go. Here we go. Here we go. Here we go. If the whole thing's a liquid, then yeah, we want to do it like this, so we can actually show the difference. Again, weak molecular forces between them. Okay, something like this, pretty much. There's still gaps between them, yeah, but not big gaps. Okay. Right. Here we go. We'll fill up the entire thing pretty much with water, but I want to show this. Yeah, random arrangements. Draw in contact with each other, sort of. You can actually see how they move. This one have a regular arrangement in the skis, yeah? So I'll leave this with you. Now you can actually see the gaps there, so the way water can flow over each other. Now here we need to draw this one. What we need to have, we need to add 4 there. We got 40, we got 20 there. This be 0, and then this will be 10. Wait, 10. Okay, let's do 60 there. So this will be 30. This will be 50, and this will be 70. Okay, now this is the cooling curve. How do we know if it's a cooling curve? Because it tells us that it goes from 80 to 30 to 20 in this case, and it also tells us it cools down. Now, what are we doing? It is freezing at 30 degrees. So therefore, at 30 degrees here, it freezes. I mean, the line is going to be flat at 30 degrees. It's going to be flat there. So this here is what? It's flat line. So this will be freezing. Okay. So this means that gallium is in liquid state. So pretty much above this is going to be in liquid state. Okay, so this will be liquid state. I'll write down liquid state. Now we don't know what's going on above that, so just leave it there. Yeah. So temperature sample is at this much. Initially is this much. That's the starting temperature, and then temperature cools down to 30, hit 30, and then start to freeze. We don't know how long. We don't know how long it freezes, and then eventually after that, the temperature drops down again to 20 degrees somewhere here. Okay, so somewhere here. Here we go. So somewhere here. Okay, so somewhere here, final temperature. The final temperature of solid, the temperature of solid is this one here. So therefore, this is solid, and the final temperature is 20 degrees there. Okay, and the line just ends. So I'll just end the line over there, pretty much. You can see 20 degrees. Done. 3 marks. Now this is the centripetal force. Now the centripetal force, if we don't know what it is a resultant force. It points inwards towards center. Okay, so it is the thing that prevents you from going in a straight line. So the resultant force that prevents you from going in a straight line. Therefore, the answer is going to be D in this case. Now the question is, the speed is constant. Why is it? So here we got the center, we got the string, and the object is going around and round and round and round and round and round. Okay. Now this is the object. So the object going this way. You got the string. The object is going this way. You got the string. The object going this way, and so on. Now, the speed is the same. So, for example, if this here is 20 meters per second, here's going to be 20 meters per second, here's going to be 20 meters per second. The question is, why is the velocity changes? Now, velocity is a vector. So, velocity equal to vector, which means that it has magnitude plus direction. And the direction is changing. Direction changes. That's why the velocity changes. Okay, that's only 1 mark. That's enough for that. Okay, now we have another equation here, nice one. So we've got the mass done. We got the length and the velocity. This one, we've got velocity there. The force, external force is this one. We've got F, and we have it come to rest. So therefore, we got U. So therefore, it lands on this with velocity V. So this will be final velocity. You can actually see that when we read the question here, I'm just writing the stuff that we know. We know mass M. V, I didn't know it was V earlier. And then when it tells me that it comes to a rest, I know that U will be rest. So therefore, speed is 4. Okay. Now work out the time. So we're looking for the time. So T, here we go. So what I need to do is I need to work out this one. So what I need to do now is I need to rearrange it. Therefore, it's going to be time equal to change in momentum. Okay. Now what I'll do, so this here is change momentum over time. So all we have to do is just swap force and time. So time, force. Here we go. Now, what's momentum? Again, we'll go back to the equation sheet. Again, the equation sheet is given to us. Here we go. Change momentum. Here we go. So mv, mu. So therefore, we go back with that because they're giving us everything. Yeah. So if we can't do this, then what's the point? Yeah, because they give us the equation as well. So we want to be able to get those free marks, and they're for free. Okay, you get them. So mv minus mu over f. Now m we know is what? 53. V we know is 4 times 4 minus 53 times 0. Now why do we know it's 0? It's rest. Rest is not moving. Rest is 0. So this is 0. And then the force divided by what? The force is 3. Okay. Time. Now plug this in your calculator. So this will give me 2, 1, 2, 3, and that's the answer. Look, I'm just typing this into my calculator there. Okay, let me just type this. So 212 divided by 3500, and this gives me 0.0656 second. Okay, and is this the answer? Ooh, the questions give you answer to an appropriate SF. Okay, now that's too much. So what I will do is I will give this to 0.061 SF. So therefore 0.061. Now why 61 is because if I look at the numbers there, how many figures do we have? Let me use a different color pen there, so this way you can actually see. Yeah, I'll use this one. How many figures do we have? We have interesting. How many figures do we have? We have 1, 2. Here, how many figures we have? We have 1, and look, they've added the 0. That's the second figure. Here, how many figures we have? We have 1 and we have 2. Yeah, these are just zeros. We don't count the zeros here, but here we count the 0 because there's a dot and a 0. There are 2 figures. So therefore, my answer has to be in 2 figures. Now, this is something that I don't think you learn this in physics, but you learn this in maths. Yeah, appropriate SF. Okay. So if you got this wrong, now you know. Okay, here we go. This question, exactly this question. So this one here, same as your September one. Okay, now if you did your September purple pen 100% properly, then you will get this question right. Yeah, so if you done your September question properly for this question, then you will definitely get this right. If you got this wrong, then you need to do it properly. Okay, now let's take a moment to have a read of this question. We got 2 trolleys. Yeah, we got trolley P and trolley Q. Now they have the same speed. They're going towards, here we go, V and V. They're going towards each other. Now they have the same mass. Now when they collide, they stick together and they stop. So we know they stop. Okay. The question says how momentum, first one, is conserved in this collision. Second question, how energy is conserved in this collision. So therefore we have 2 things to talk about. So we're going to split this into 2. Okay. So we have momentum to talk about. We got energy to talk about. Okay, and let's get started. Momentum. What do we know momentum? Momentum means the conservation law of momentum. So, okay, you know what? I'll not do that. So let me just go straight. So we know that the total momentum. So momentum is P. Energy is capital E there. So total momentum before a collision must equal to total momentum after a collision. Again, so no external forces applied. Okay, that's momentum. Now energy, we know energy can't be created / destroyed. Okay, only transferred from one store to another. Okay, so now we have this. Now we can start. we got before and after. Now before must equal to after. Now before we have momentum of, so momentum P of P, momentum of P plus momentum of Q. This must equal to momentum of P plus momentum of Q. Now momentum of P, we know it is going to be mass times velocity. So this here will be velocity of P plus mass times velocity of Q. Plus, now what we have is when they collide, they stick together and stop. So therefore, they're going to stick together and then they stop. So therefore, we will have the same thing there. So since they stop, they stick together. Okay, so stick together. So same thing, P plus stick together and stop. Now, here is the juicy part. Before is mv plus here. Now the velocity for the q. Now q is going in the, what is it? It's going opposite, the opposite direction. Therefore, p is, so if this is positive, q is going the other way, so q will be negative. So therefore, q will take a negative instance there. Q will be negative v. Okay, q. So therefore, this is v. Now I can, because they have the same mass, same velocity, so plus minus v. So this goes to 0. Okay. Now this one here, this what happened is the velocity. So they both stick together and they stop. So therefore v goes to 0. Plus this goes to 0. So the whole thing goes to 0. Equal to 0. Therefore, what we can say here we go. So therefore, this applies to what we said. So therefore, we can say therefore momentum is conserved because the momentum before a collision is the same as momentum before after the collision. Therefore, this will be unit kgm/s kgm/s. Okay. Now we are going to apply the same thing for energy this time. Now energy we got before and after. We need to do the same thing. Yeah, look. So many people have just done the before. We need to do the after because they collide before and after is the one where they stop. So we need to do this before. Again, so we apply the same thing before. After. So the kinetic energy we had before, it needs to be the same as the kinetic energy we have after. Now we got kinetic energy, so we'll call this Ke of P plus Ke of Q equal to Ke bottle. Q. So this would be half mv squared P plus half v squared Q. Now here we know that the v squared goes to 0, so I'll just put this there, v squared. Now v squared goes to 0, so v here, so v goes to 0, so this automatically goes to 0, so this is 0 joules. Okay, now this one here we got v squared plus this half plus halved. Okay, now the speed is they are going opposite each other. So therefore, we need to factor in is the negative. So v squared plus so we need to factor in the negative. So this will be negative there. So this cancel out. This goes to 0 joules. 0 joules. 0 joules. Okay. All right. So therefore, before the collisions, the total energy. Okay, my bad. Let me just do something. I think I did a mistake there. So let me just delete this. Energy scalar, so the direction doesn't matter. Okay. So therefore, if we add them together, so this would be mv squared there. Okay. Now the question is, how can we go from mv squared to 0? So how did this happen? So how do we go from energy? So at the start, both of them are moving. Yeah, they're moving. So they're moving against each other. So the sum of that, they have kinetic energy. Yeah. So yeah. So again, so my mistake was energy is a scalar. Okay. So the direction doesn't matter. So the sum is there. Now afterwards it goes to 0, so this makes sense. The velocity goes to speed goes to 0, so therefore the energy at the end after the collision is 0. Now the question is, how is this conserved? So if we got this much at the start and at 0 we have at the end we have 0, then where is the loss? So therefore we can have the kinetic energy, okay, gets transferred to thermal energy store, okay, via heat plus sound. Okay, pretty much. Okay, so dissipated to surroundings. Okay, now if you think you put this one in, let me know, because I think I remember someone mentioned something about that, but I don't think I'll give you the mark there. Do let me know. But this is how it happens. So we need to mention this at the end. So what happened is the energy. So for momentum is a vector, so we need to factor this, the vector. So momentum is a vector, so we need to factor this in. Vector, so we need to factor this in, and then just like I got confused earlier, we need to double check our work, because like I was doing this and I was, wait a minute, energy is a scalar, so why am I doing the negative there? So that's why I went back and deleted this. So therefore you add them together, you end up with this one, so therefore you have kinetic energy at the start and before, and then you got to 0. So what must happen? This must happen in this case, yeah. So it means, so all that kinetic energy must have been transferred to the heat, thermal energy by sound. Okay, so hopefully this makes sense. Now multiple choice. Now which one describe through the wall? Now through the wall. Okay, so through the wall. Now let's go. Conduction through the movement of only wood only. So this is incorrect. So there's a word only there. That's not correct. Conduction through the metal by ball vibration particles and movement of electron through the steel. Okay, through the steel. Ball vibration. This is steel. Conduction through the woods. Okay, so we've got the wall made of wood and steel. Okay, so the wood by ball vibration. So here, ball vibration movement through the wood, through the wood. Okay, convection through the metal by the movement of electron through the steel. Convection. Yeah, I don't think that's correct. All right, so therefore the only one that makes sense. Okay, convection. No. Conduction through the wood by ball vibration of the molecule through the wood. Okay, conduction through the steel metal by both vibration particles and movement of electron through the steel. Now it has to be B in this case. Okay, now this is the way thermal energy is transferred through the wall. Okay, because the steel has electrons through it, that makes sense, and vibration particles as well. Okay, and metal is a good conductor as well, so this will conduct heat better. So yeah, all right, so good. Now which one is a good use of sound? So this is sound. Now optical, this uses light. Okay, so it can't be this one. Sunbed uses light, so it can't be sound. Fluorescent tube uses light, so it can't be this one. So therefore by default it is A. Okay, Alright, sound. Look, there's the word sound and ultrasound. So you don't know an answer, you can go with the process of elimination. Somebody uses light. Optical, the word is optical there. It uses light. Fluorescent tube is fluorescent, it uses light. So the only option is left with cleaning jewelries. Now this is a good question there. So this is something that you guys have done before. Okay, density. Again, you don't know the equation. Yes, you do know the equation. The equation is at the back. So density is mass over volume in this case. Now the mass is what we have. We need to be careful with this. We've got the mass of this. We've got the mass of this. So therefore we need to take them away. Okay, so take 55. The volume is how much? We got 20 here. We got 35, I think. 35 there. So therefore 20. So therefore you just plug this into your calculator and you let me know how much you get. Okay, so the answer is 2.5, which is a C. The answer is C in this particular case. Okay, let's go next one. Here we have a question about moments. Alright, now what we have is let me just make this a bit larger. We got something like this. We got the center here. We got the pivot. So this is the pivot. We put triangle there. Force goes down. This is 50. Okay, now 50. How far is it? And then we got this here going this way. So this distance is 40 centimeters, and the distance from this force to here is 4 centimeters, because the whole thing is 8, because 4. Therefore, what we have is we got force F. What do we need to do? We need to do. What do we need to do? We got clockwise equal to anti-clockwise. So therefore, we got this one here that pulls it down. Want to go this way? So this is anti-clockwise. So anti equal to clockwise. So therefore, we got FD equal to FD. So FD is this times 4 equal to F times 40. So we're looking for what? 50 times 4 divided by 40 is equal to F. Okay, it's equal to F. So therefore we end up with 5. So the answer is D. If you got this wrong, here's the working out. Make sure it's there. Now we have which is detectable. We got a gold sheet. We have oh, this is the this is the Rutherford, I think. Rutherford experiments about the alpha particles and the nucleus, which can be detected from this. Neutron has no charge. Wrong. Electrons around the nucleus. Wrong. Wrong. The answer is A. Nucleus very small. Nucleus very small. So that's why when it goes through, it says most of them just go through. Few of them hit the nucleus and get deflected. Yes, because the nucleus is very, very small. We did this, I think, this year, last year, year 10. Alright, now here we go. What we have here. We have spring, we got annex, okay, we got original spring, we got new length spring, so we can work out the extension. We got force there, we got new forces. What's going on? Okay, so let's work out. So F is equal to KE. Now we need to work out K. K is equal to F over E. F is 6, so this is going to be 6 take away 30. Okay, this will give me a spring constant. So how much is my spring constant? Okay, so the spring constant will be 0.667. Now I need to have another one again. So I got F is equal to KE. I got F. I'm looking for new length. Sorry, looking for new length. So new length would be E is equal to F over K. F is 6. No, F is 2 this time. Yeah, F is 2. K is 0.117. Okay, this will be 12. Okay, E is 12 centimeters. This is the extension. Now we need to find the new length. The new is equal to 12 plus 30 equal to 42. So the answer is C. Okay, we're looking for the new length. All right, C. Now compression. Yes, we got compression. So this is compression. This is rare refraction. Which type is the sound wave? Sound wave is longitudinal waves, and at X we got compression. So compression. Therefore, the answer is going to be A, because longitudinal waves sound. Remember how many times I got you to write it. If you got this wrong, then I need to make you write again. Okay, now potential difference, charge, time, energy. Okay, so what do we need to do? What do we need to do? We got charge. I'll go through this in 1 second. We got the energy. We got, okay, so we got voltage is potential difference is energy per charge. Okay, energy is 20 divided by 0.4. Okay, got 50. Got 50. Got 50. Got 50. Okay. Now what we need to do is we need to remember. So this here is in 1 second. In 1 second. So this is in 2 seconds. So what we need to do is we need to make sure that this here is in 1 second. So therefore this here is in 2 seconds. This is in 2 seconds. We need it in 1 second. So therefore in 1 second it's going to be divided by 2. This will be 25 volts. Therefore is C. Yeah. Nice one. Let's move on. How does frequency get redshifted? Okay, redshifted. Now, redshifted. What does redshifted mean? So, redshifted means the wavelength equal to longer. So, if the wavelength is equal to longer, it means the frequency is shorter. The frequency is shorter. Yeah. So, if it's long, it means that it's going away from us. So therefore, we got one option, two options. So it can't be this one, it can't be this one. Now we're left with two options. Now, the frequency is less. Yes, it's shorter, it's less. Here we go, done. A. Move to the next one. Lake. Density is less. So okay, an underwater lake, underwater river diver moves from the ocean to the fresh waters. Okay, so lake, ocean. Okay, we got this, got this. The density of the lake is less than the density in the water. Okay, so density here is less compared to the water. In which position does the diver experience the smallest pressure due to the water? So, in which position does the driver experience the smallest pressure? The smallest pressure. Now, remember, the deeper you go, the pressure increases. So, if the diver is here, yeah, so density is bigger here in the water, so there'll be more pressure on the guy. So here, the density is the less. The density, now remember the equation, pressure is equal to rho this. The density is less, yeah, but still deeper, so we still get some pressure, yeah. So here, it's going to have to be C, yeah, because it's less dense, so density is less, so pressure will be less. So if the height is less, then the pressure will be even less, so it has to be this one by logical reasoning. Now, come on guys, we know this one. So here, remember, we got this line, we got parallel, so this parallel, 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 parallel. We got this one, we use our ruler, we got parallel as well, we got parallel, 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 parallel. So therefore, the resultant force will be pointing will be in this direction here. So this is the direction of the resultant force. So the object will be putting in this direction. That'd be too much there. Here we go. So therefore, the object will be pointing in this direction. So this is the one we need to work out. So the answer is going to be A in this one. Remember, we spent time with like scale diagrams with rulers sliding it. So this is this question. Okay, here we go. Now here we need to label what we have again. Compression to compression. So we got. So this is a compression. This is a wait a minute. So 1, 2, 3. So this 1, 2, 3. So the big compression. Let me just put this properly. So compression, compression, here to here, compression, here to here, compression, here to here is compression. Okay, and then we've got refraction R. So therefore, what we have from here to here, this is a wavelength. Okay, and likewise, we go from here to here, this is a wavelength. So from here to here is a wavelength. So therefore, the answer from here to here is a wavelength. The answer is going to be B. Okay. Right. Alright, so this is a good question there. Now, we know that pressure is inversely proportional to V. Okay, so therefore we got P. Yeah. So if pressure, sorry, the volume increases, therefore the pressure goes down. So we know the pressure goes down. So it can't be this one, it can't be this one. So you're left with these two options. So this one and this one. Now what happened is the volume was at 20, and then we've increased it by 1 by 40. So therefore the new volume is now 60. Now, by how much has it gone up? It's gone up by 3. Yeah, so from 20 to go to 60, that's a new volume. Yeah, so the volume initially, look, the volume initially was 20, but now it's gone up to 60. So yeah, because this difference is 40. That is the difference there. So it's gone up from 20. Now the new volume is how much? 60. It's gone up by 3 times. Yeah, so if the volume goes by 3 times, the pressure will go down by 3 times. So therefore the answer is B in this particular case. Okay, so hopefully this makes sense. Again, this is logical. Now what we have here, okay, now we go from fusion, so latent heat of fusion. So this is when it is changing state. Okay, so if we go from here, 3 goes from 7. So therefore the time it took for him to go there is 4 minutes. Okay. Okay, fair enough. Now what we have, we're looking for latent heat. So we've got Q, go to ML. Okay. We have, so we're looking for L, let's go to Q over M. Okay. Now Q we know is 2, this joules per minute. So what we need to do is we need to multiply this by 4 minutes. This will get rid of the minute divided by the mass, which is 200 grams. Now I don't need to convert the grams because the answers are in grams. So this will give me 40. So the answer is going to be B in this case again. Now why did I multiply by 4 minutes? Because the questions give me the number in per minute. So therefore joules per minute times 4 minutes. You can see minutes and minutes cancel out. So now I'm left with just joules on the top and just multiply by 4. Done. Hopefully this makes sense. Now, which one is used to remote control TV? That is too dangerous. That is too dangerous. This is too long. Too long. Long. Therefore, it is this one. Remote control, guys. When you press the remote control, if you look at the little light, it's red. Yeah. I think everyone has the remote control at home. So do check it. Yeah. Do check it, guys. Do check it. Do check it. Alright, now question 23, there's 2 ways you can do it. I'll show you a quick way, the way that we know. You've got 2 ways, you can use Suvat equation or you can use what I'm going to use here. Now the skid's going at 3 meters per second. Apply the brakes, so all that time brakes, let me use the change here. So apply the brakes from here to here, brake until it goes to 0, yeah? Now, so here, to apply the brakes, they need to have what? Braking force, so friction, braking force, yeah? Now, the work done against the braking force is the change in kinetic energy. So what happened is it's change in kinetic energy equals to the work done, and that goes against the braking force, yeah, because you need to do work against that. Okay, now what we can do is we can calculate the change in kinetic energy. So now we know that here at the end the kinetic energy is going to be 0. Why is 0? Because the speed is 0. Therefore we can just work out the kinetic energy. So kinetic energy is half mv squared, half times 60 times 3 squared, and this will give me, okay, this will give me 270 joules. Okay, so therefore the change, so at the start this is the energy, so after is 0, so therefore the change in kinetic energy will be the same. Okay, and this is going against the breaking force, and this here, the change kinetic energy, is equal to the work done. So change kinetic energy is 270 equal to work done is force times the distance. Now the force is going to be against, because it's the same as applying the breaking force. It's going to be the force there. So therefore, 270 equal to force times distance we know is 5. So therefore, 270 divided by 5 equal to F equal to 54 newtons. Okay. Now, yes, you can use the Suvat equation. For example, you can use the V squared is equal to U plus 2AS. You can use this one to work out the acceleration. So this way you know what is the acceleration in this case as the guy is breaking down, and then you can use this to work out F equal to MA, the resultant force in this case, because applying the brakes, what's happening, blah blah. Maybe you can do this one because I've seen some people do that, so that's fine. Okay, again, if you got this wrong, here's the full working out, and hopefully you've heard the explanation there. Now this is a good one. So we have, which angle is the refraction? Okay, so the angle of refraction. What angle is the angle of refraction at the surface xy? Xy is here, x and y. So which one is the angle of refraction? The angle of refraction is this one here. So angle of refraction. Okay. Now the dotted line. What is the dotted line? The dotted line is normal. Okay, so that is D. Now which one changes? Okay. Now here we go. So refraction. So whenever it's changing medium, so what happens is changes. So what changes is the speed changes. Okay, and then the wavelength changes. Okay, right, now the same, what stays the same is the frequency. Okay, so therefore the answer no, 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 B. Yeah, because what happens is if I have a boundary like this, I have a wave 1, 2, 3 bends, 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 bends. Okay, now look at this here. The frequency, so the number of wave that's passing the point is still the same. So here, there's one wave passing the point. There's only one wave here. Here, there's only one wave here. There's only one wave here. There's only one wave here. So the number of waves that pass the point is still the same. So that's the frequency. But what changes is the speed, because it is bending here at this point, because there's a change in direction here. Okay, because the wave is crossing the point at different times. So this causes a change in speed. Okay, and when this causes a change in speed, this causes a change in wavelength. Okay, right, because the wavelength will be different compared to the top if I'm drawing properly. Okay, now we have reflection. What's the low reflection? The low reflection tell us that the angle of incidence equal angle of reflection for a plane mirror. Okay, so now we need to draw the normal. Okay, so this is 45, this is 45, this is 45, this is 45. We need to draw the normal. Okay, now if this is 45, this is 45. Okay, this is 45. Now the question is the angle between PQ, where's P? PQ, okay, and QR, where's QR? QR is what? Is 45 degrees. Let's have a look. The angle between PQ, okay, and Q, wait, QR. Okay, so the first one's talking about, so it's telling us that PQ, so the angle between PQ QR. So it's telling, so this angle here is 45 degrees. No. So the angle is 90 degrees. Now, angle between QR and RS. So QR and RS, this angle here is 180. No! The angle between, yeah, that's just rubbish. The answer is D. By default, we already calculated the QRY. Wait, QRY. So QRY. Yeah, that's correct. Yeah, it's crazy there. It's crazy stuff. Okay, energy supply is this much. Okay, alright, so this is the total energy. Out of this energy, this is transferred to the surrounding, so this is waste. This is used to heat the casing, and it's also waste there. The remaining energy is used to heat the water. What's the efficiency? Oh my god. Okay, so useful equal to total takeaway waste. So 600 takeaway. Joules. So efficiency is useful over total times 100%. So useful over okay, so the answers are not in percentage, so I can just get rid of that percent. I can get rid of that. Okay, so therefore the answer is just going to be, come on. Okay, my pen has changed color. Okay, the answer is B. Okay, alright, now let's have a look. So black. Now black. So black, dull, matte black. They're good at absorbing heat, but they're also good at a good emitter of heat. Yeah. So this means that if the heat, which is here, been going outwards, okay, so the black part is going to absorb it first. Okay. So once the black part has absorbed it for some time, it's going to radiate it afterwards. Okay. So therefore the answer is going to be A in this case. Now, white on the other hand, or even shiny in this case, so shiny white, they are a good reflector. Now, reflector means, so here's the surface, the heat gets to the material and the material will reflect it straight away. Yeah, the material will reflect it straight away. But black or matte in this case, what happens is the heat goes in, it's going to absorb it because it's a good absorber, absorb it, and then later on it's going to emit it. Yeah, and that's the difference between a absorber, an emitter, and a reflector. Reflector would just reflect it straight away. Go, boom, go up. Boom, go up. Reflector. Okay, that is what we need to understand. And this is in terms of heat, yeah? Now, this is a good one. Now, first of all, we have a diverging lens. How do we know it's diverging lens? Look at the arrows. They are diverging. So therefore, what we're going to do is we're going to get a virtual image. So we need to go backwards. So this line here, we need to extrapolate the line. Okay. No. Yes. Okay. So therefore, the lines need to be extrapolated. Therefore, we're going to go backwards. Now, normally you're going to use a ruler for that, yeah? There we go. So therefore, the point where the dotted line meet up with the second line, so this is 1, that's still 1, so the 1 goes backwards, Okay, so this is our focal point. So the line where it meets, so this would be my image here. Okay, it's my image. Now the image is upright because standing up. It is virtual because it is formed behind the lens. So if you're looking here, you can only see this small version through the lens. So it is virtual. Okay. It's upright, it is virtual, and it is small. Now, which one is the prime? Now, virtual image, we've got 1, 2. Now, it can't be Q because Q is there, so therefore it has to be P. Now, if you do this properly, you use a ruler, yeah? So when you extrapolate it, you will see that it goes to P, yeah? It goes here. So therefore, the focal point, the primary focus is going to be P in this case. That's why we need to draw it properly, okay? Now you know how to draw it. If you got this wrong, make sure it's fixed up. Now here we go. So we did this one earlier. So this is the point of limit. This is the limit. This is the limit. Why? Because look at this point. Afterwards, it start to curve. Look at that. Start to curve. Start to curve. Yeah. Limit of proportionality. Okay. And that's it. That's it. That's the end. And everything else just the equation. Look, all the equations given to you there. Yeah, kinetic energy equations there. Work done equations there, power equations there, everything is there. Look at that. This one's there as well. Everything is given to you. We just need to know how to use them. Okay. And look, let's take a look at the calculation question where you need to calculate. So look, so this, I mean, multiple choice is just 1 mark. Let's look at the main questions where we have marks. Come on, multiple choice again. I mean this one, if you already know from the September, this, okay, look at this one. So this 3 marks. Yeah, three easy marks. That's 3. Let's keep it going. There's, look, that's all 3 marks again. Okay, so that's 6 marks total. Look, 3 marks again. You just minus there. Okay. Let's keep on going. Nothing to calculate there. Okay, look at that. 3 marks. 3. Why is it 3? Because you already said you're ignoring it, and you just need to calculate the mean. The mean is the average. Okay. Okay, look, 3 marks again. Because the equation is given to you, and this is also going to be 3 marks there. Why? Because look, they even tell us how to calculate the circumference of the circle, 2 pi or radius, and they tell you it's a quarter as well. So this is 3 marks. Look how many marks you're getting. Yeah, so 3. Keep going. Look, another one here as well. Look, another one, 3 marks. Now, why this 3? Because they are giving you the equation. So you just need to put the equation, convert the numbers. Okay. Here we go again. 3 marks. You just need to. So now here, you need to convert this one. That's 3. Okay, that's fine. Okay, that's 1 mark there. Okay, look, 3 marks again. Now this is telling you, so from the origin, so you know you need to do the difference there. So you can actually see that you pick up a few marks there. Again, so we need to make sure that we know which topic we are lacking behind, and make sure that we get better at those topics, and that we're ready for the final one. Okay, so hopefully this helped you out.